thermoelectric effect, things like that. That's basic definitions of how these principles work. Of course, in the due course of time, we will be learning it indirectly. But as a subject, as a topic, you study that by yourself. That's self-study. Okay. So module 1 is over. Module 2 we are starting today. Module 2 starts with the potentiometer. Potentiometer is basically used for measuring either linear or rotary motions. Okay, linear motion or rotary motion. Quickly some basics. Anyway, that's we generally do. After this is just a thought for the day. Displacement is distance plus direction. Velocity is speed plus direction. So acceleration is what plus direction. What do you call that as? What plus direction is acceleration? Think. What is it? What is that called? Rate of change of velocity is acceleration. That's not that x that we're talking about. But anyway, think about it. We will discuss in the next class. Sorry? Yeah. No, that magnitude we call it as distance in case of displacement. So distance plus direction you call it as displacement. Speed is not a vector quantity, it is a scalar quantity. Speed plus direction is velocity. What plus direction is acceleration? Pulse. It's not pulse that you are close up. Okay, just refer. Just to create some curiosity to know that. It's not very difficult. Just Google it out or find out if you will be able to find. Right. The types of motion you all know very well. This is a translation from position 1 to 2. This is pure rotation. You have an axis about which it rotates, and this is translation plus simultaneous rotation plus translation. And we will be mostly talking about either pure translation or pure rotation. Pure translation and pure rotation only we will be able to measure in the transducers that we will be discussing now. Why we need to measure displacement? Because we are interested in the displacement of some things. For example, you take CNC lathe. We want to know let's say we are doing a turning operation. From what position to what position? Let's say 35 mm you have to do turning, step turning, things like that. So you need to measure exactly 35 mm in the process, so you need to measure the displacement. So that's one thing. Second, very special about this displacement measurement is displacement is acting as a secondary transducer for many of the parameters like temperature, force measurement, torque measurement. In all these cases, the primary transducer will transduce the force or torque, whatever it is, into a displacement, and you should have a displacement measuring device to measure what is the displacement, and then you calibrate that in terms of what are the original parameter. If the original parameter is velocity, you put velocity. If that is pressure, you measure pressure. If that is force, you measure in terms of force and things like that. Basically, the physical parameter in many cases, not all cases, many cases, translated into or transduced, not translated, it is transduced into a displacement, and you need a displacement measuring device to measure the displacement of the primary transducer. So basically the displacement measurement or the sensors which are used for the displacement measurement will act as secondary transducers. In that case, measurement of displacement is very crucial. You should know a lot of sensors. In our syllabus, we will be talking about 3 sensors only. The rest all you will study by yourself because it's an undergraduate course. They are not included much. If you are very much interested, you refer my book. I think about 20 different displacement measurement devices I have discussed. But we will be discussing about potentiometers, the subject matter of today, LVDT tomorrow, and then an encoder. Encoder, widely used sensor in CNC machines and other things, encoder. Okay. And of course, as part of the second module, they also have accelerometer that is used for accelerometers and gyroscopes that's used for measuring vibration and angle of twist. That's the end of the so for displacement wise, only these 3 sensors we will study in detail. So today we talk about the potentiometer. Here we have People thought, what are all the methods by which we can measure the displacement? The primitive electrical components that they had was, the components they had were resistance, capacitance, inductance. These are all the primitive electronic components. So they thought how to make use of this resistance to use that as a transducer for measuring either linear motion or rotary motion. The result is the potentiometer. Okay. So basically, what happens in the resistance circuit? You take a resistance circuit. If the current flows through the circuit, whenever it encounters the resistance, it loses some amount of energy. It becomes tired. The potential gets reduced. So if you take a multimeter, put it in voltage mode, put one probe before resistance, one probe after resistance, connecting like that, there will be a potential difference. Or you take a runner, there's a hurdles race, 100-meter hurdles race. Let's assume you have a meter to gauge one person's energy. Before starting the race, you measure this energy, this potential. After running 100 meters hurdles race, you measure this potential. He would have lost some potential in the process of running the 100 meters hurdles race. Same thing happens inside the electric circuit, and electron loses its potential. Not electron. There is a potential because of which the electrons flow, and that potential is lost for in the circuit. So there will be a potential difference between these 2 points. The potential difference will be proportional to the amount of resistance that it encounters. If it is a 100 meters hurdles race, the fellow will be little tired. If it is a 400 meters hurdles race, he will be more tired. If it is 1000-meter hurdles race, of course you will be dead by the time you go there. So it depends upon the amount of resistance that he encounters. The potential difference is directly proportional to the amount of resistance. This law is what? V is equal to IR. V is equal to IR is what? V is voltage, I is current, R is resistance is what? Which law it is? Ohm's law talks about only this. So voltage is directly proportional to, voltage is potential. Okay. Voltage is directly proportional to the resistance. V is equal to IR. Of course, the directly proportional to current, and the constant of proportionality is R. And when you are keeping the current constant and varying the resistance, the other way also you can give it proportion. Okay. Fine. So V is equal to IR, and V and R are directly proportional. If R increases, the potential difference increases. Potential difference is what we call it as voltage. So here we will be making use of that Ohm's law principle for measuring displacement, either linear displacement or rotary displacement, using the device called potentiometer. Potentiometer is the device that we need to learn. Okay. Now, I don't have a watch with me. At 5 minutes before the bell, you just give me a hint so that I'll wind up properly so that we will not exceed it. Potentiometer, many of you would have seen the small pot. They call it as pot. Potentiometer, first 3 letters pot. It's not an acronym, but that's how shortly people call it. So it's a pot. You would have seen a very low cost. So you can use it as a rotary transducer. That's very cheap. Of course, linear potentiometers are available, a little costlier than the rotary potentiometer. However, much lower cost than other sensors. Okay. So cost-wise, potentiometers are the cheapest one. Cheap is not the right word. The low cost one. Okay. Cheap means quality-wise is also bad. You call it as a cheap. Cost-wise is also low. You call it as cheap. It is not. Of course, it is not that cheap, but it's a low-cost transducer. So low-cost transducer is potentiometer. This essentially will have a resistive element, a power source, a sliding conductor wafer, very important element, and a voltmeter. Of course, voltmeter I said because you will be able to visualize it because you are all mechanical students. Basically, there is a voltage measuring circuit. It need not be a voltmeter that I have depicted here. That's only for visualizing. Okay. So there will be a voltage measuring setup, and then a mandrel. Mandrel is not mandatory. That's optional. We will see on the first slide. This is the potentiometric basic circuit. Okay. You have a resistive element. This basically a high resistance material. We'll talk about that more. And you have connected a power source. Okay, that's the excitation. Okay, and in one end of the resistive element you are connected to the voltage measuring device. The other end is connected to something called wiper or the contactor. Okay, so you will be measuring the potential difference between one starting off the resistive element and the contact or the wiper that we have. Alright, so as the wiper moves towards right from left hand side, the resistance between the two contacts increases, and proportionally there will be the voltage difference. So proportional to the resistance there will be voltage. That's the working principle of potentiometer. The resistive element that we have here is a pictorial view that I have shown, kind of a semi-circuit diagram. It's not an actual picture, it's not a circuit diagram, there is in between. A conceptual diagram is what this is. Okay, so here the resistive element will have protective coating. If you want to easily visualize the potentiometer device, have you seen a device called a rheostat? You might have used at least in the physics lab. Yeah, rheostat is basically a potentiometer. But there is a mandrel which is fixed on a stand, and a wire is bound on the mandrel. Okay, that we are going to see. That's not a very basic type. But the basic type potentiometer will be much simpler than that. But the wires on the rheostat that you might have seen will have protective coating. Have you seen that? You will have protective coating. So that is to avoid the wire in direct contact with the atmosphere, so that it will not corrode, erode, all environmental effects, it will not get affected. Of course, these wires are very thin, precision drawn wires. There's a drawing process. Wire drawing is a manufacturing process. It's all wire drawn of diameter of typically 50 micron. 50 micron is a small size, micrometer. 50 microns. And the material is, there are many materials commonly used alloys that I have told. Nickel, chromium, copper, nickel, silver, palladium. These are all commonly used material for the potentiometer. It should have high resistivity. That's important requirement of this. Very challenging exercise comes when it comes to the wiper or the sliding contact. The requirements of the sliding contacts are very contradictory. That's where the design challenge comes. Okay, when you are a designer designing a potentiometer, these are all problems. What are they? Or these are all the expectations from the wiper. The wiper should have good spring property, so that even in the vibratory environment, it is always in contact with the wiper. You can keep imagining the rheostat and the contact that moves on top of it. Okay, that should have enough spring property so that always it is having contact in the mandrel. Not mandrel exactly, the resistive element that is bound on the mandrel. So on the resistive element, it should always have a contact. Suppose if you are using in bus, typically any big machineries, there will be vibration. Due to vibration, the contact should not jump and leave the contact, or the intermittent contact should not be there. If you want to experience a vibratory environment, you just travel in some of our MTC bus from Tambaram to our college, you will be able to see some sound. Recently there are some good buses available, but still there are some old buses where you will find the vibratory environment you will be able to expand. Okay? Very disturbing buses. Even in that environment, the contact should not jump out of the resistive elements. That's the one. And the contact force should be minimum. Contact force should be minimum just to make contact to avoid friction. Okay. If you have used, mostly you might have used, you are not the first batch student of this university. So when you have seen the rheostat, you would have seen already there is a mark on the place where the contact is there. Many times people have done this sliding from left to right, right to left. So a lot of wear and tear, and that's because of the friction between the contact and the resistive element. We do not want much friction between the contact and the resistive element. So the contact force should be minimum. Then friction force will be minimum. So the wear and tear will be less. Okay. So to reduce the friction, you reduce the contact force. Okay. Reduce the contact force. If you reduce the contact force, what will happen? Due to vibratory nature, if your environment is in vibratory environment, then if the contact force is less, then it is easily it will be able to jump. Let's say a single contact, it will be able to jump from the mantle, instead of just touching. If you apply a little more extra spring force and keep pressing it, it will have more friction, more wear and tear, less life for the entire product. Also, another factor here, there is something called contact resistance. The contact resistance also minimum when you just make the contact. You should not press too much. Okay. So to reduce the contact resistance, you should have less contact force. To have less friction, you should have less contact force. These two belong to one team. Another team, to work efficiently in vibratory environment, it should have good spring force and more contact force, so that it doesn't come out of the mandrel or the resistive element to provide a continuous flow of pressure. Okay. So these two are contradicting requirements. So you should be able to design. Sai, I am upset. Sorry. This is third warning that I am giving. Next time you will be permanently out of the class. Alright? If you are not interested, don't come. Don't come here and sleep. This is just second hour. The conductive lubricants can be used to reduce the friction. That's one way, at least we reduce the friction. Contact resistance is anyway, you have to have less contact force. Then only you can reduce the contact resistance. Okay. Conductive lubricants are lubricants which will reduce the friction, but still it will conduct the electricity. Okay, they are all conductive lubricants. That's okay. So in Viper design, there are two contradicting requirements. One should have high spring force and high contact force. On the other hand, less spring force and less contact force. So you should be able to design both. Mandrel is needed when the let's say you wanted to measure a resistance of from this value to this value. Okay, because the resistivity is not very high. Resistivity is not very high. Then if you move the Viper from one place to another, there won't be any significant change in the resistance. There won't be any significant change in the resistance. So if there is no significant change in the resistance, you will not be able to make effective measurement. Basically, we are interested in measuring displacement, either linear or rotary. We will not be able to make. So in order to accommodate, I don't have a very high resistivity material, but I have so much of range of displacement, either linear or so much angle rotary I need to measure. How do I do that? Then what I do? With this much length of material, if I have to, my sensor has to be as small as possible. If this much length I have to do that linear displacement, it is possible provided I have the equivalent resistivity material. Unfortunately, either that material is not available or it will be very costly, but I will not be able to compete in the market if I use that. In both the cases, I will be using little lower resistivity material. The moment I use lower resistivity material, the length of the wire, resistive wire, increases. If the length of the resistive wire increases more, then what I have to do? My instrument size will be big. If I make such a big instrument for measuring displacement, whereas my competitor is making such a small instrument, normally people tend to buy the smaller instruments because they look handy, good looking and things like that. Okay, they don't want big stuff for measuring displacement. Okay. So I'll be losing edge on that. So people wanted to have a large range with low resistivity or low cost material, but still look small. They thought what to do. Okay, they have done some sacrifice, then at the cost of the resolution. They done some sacrifice on the resolution, and then took the wire and wound on a tube. That tube is called mandrel. It can be a plate, it can be a tube. Basically, it is a material. Okay. Typically, it is the electrical insulator. Typically, it is a electrical insulator. They wound on that one by one. And now it will look like exactly your rheostat that you have seen. There is a mandrel and wire is bound. That's how the wire wound resistors took the name of mandrel. And the rheostat. There is a mandrel. So mandrel is basically the holder, which is insulator, which takes the long length of wire into a smaller space. Mandrel can be cylindrical or flat shape. Of course, it should have low coefficient of thermal expansion so that it stays dimensionally stable. And ceramic, molded epoxies are some of the examples of the material that we use for mandrel. Okay, so that's about mandrel. You have displacement. Displacement results in change in resistance in potentiometer. The change in resistance results in change in voltage. Change in voltage you measure as a voltage, and you calibrate it in terms of displacement. You will be able to measure the displacement. That's the block diagram explanation. The linear potentiometer circuit diagram I have shown. This is a rotary potentiometer circuit diagram. Here you have one end of the potentiometer, resistive element. It goes like to the other end, and here you have connected to voltage source, the power source. The power source can be AC or DC for potentiometer. Whereas for capacitance, inductance, in some other transducers, DC you cannot connect. You have to have AC. But for resistances, be partial about the type of power supply that you connect. DC power supply is normally DC, so you connect a DC power supply. Here you have a potentiometer, and that's get connected to the voltage meter. One end to the one end of the potentiometer, other end to the wiper. As wiper rotates from 0 degree to 360 degree, you will be able to measure the change in resistance, and change in resistance will result in change in potential here, so you will be able to measure the voltage proportional to the resistance. Alright, so that's a potentiometer, typically you call it a spark. This is other design variation. What is other design variation? If you are not able to, hello sir, sit properly, drink water before the class, you have 5 minutes break. In class you should not eat, drink. This is not Harvard University where you can come eat. This is an Indian university. We value the value systems more. Keep it inside mind. Class is going on, you keep your leg like this and keep drinking. This is the way to sit in the class. Keep it inside, quick. You have multiple, in one rotation, if you are not able to cover the entire rotary displacement, then you have multiple turns. You have one turn, second turn, third turn, and you go like this, so that more number of rotations, the entire range of rotation you will be able to measure. Right. There is a way to sit in the class. There is a way to listen. Okay. This is Indian University. You should behave like typical Indian student. If I am teaching in US or UK, I may not expect that. In fact, I have not gone there because I will not be able to do that job there. This is a typical specification. I have just copied from one of the manufacturers listed there. You just have to go through it. There is nothing to explain there. The terms used here will be the terms that we have already discussed in the characteristics of instruments. There we have taken all the terms and discussed one by one in great detail, so you will be able to follow this. There will be minor difference because of manufacturer's ignorance, or the commercial practice may be slightly different from academics practice. Because of that, there will be terminology, mild difference will be there from manufacturer to manufacturer, mainly due to manufacturer's ignorance, because if he is well educated and very knowledgeable person in the field and running a company, the specification will use proper technical terms. Normally MNCs will not have any mistakes on their specifications. Some local manufacturers, simply out of experience they make, but they are not even good at English. They are manufacturing, but they may have skill in developing that particular sensor. If they sensor and then sell it, probably you will find a lot of difference. and there will be some difference in usage from area to area, that also will be there, but eventually you will be able to make out what they are trying to say once you are familiar with the characteristics. Typically you see the tolerance on linearity. It's basically they are telling linearity. There is nothing called tolerance on linearity. Linearity itself is conveys what it is. Okay. Whereas this is tolerance, there is some other tolerance. Tolerance on rated resistance is actual tolerance. What is that? They know they cannot make, if it is a 10 ohm resistive material, exactly 10 ohm we may not be able to make. So the designer itself gives the variation of 5% on that particular resistive element is allowed during the manufacturing process. That is tolerance on resistive material. There is nothing called tolerance on linearity. Linearity itself is variation from the actual value for linear instruments. It's accuracy for linear instruments. And this particular device is a linear instrument. The moment there is a displacement linearly proportional to the displacement, there will be a change in resistance and change in voltage. Okay. This particular, they somewhere said it is linear. That is that all climatic condition, power, tolerance, resistance behavior is linear. Resistance behavior is linear. Not all potentiometers are linear. There are potentiometers which are non-linear. Okay. So this particular potentiometer is linear. They said it is already linear instrument. Then they cannot use accuracy. Sometimes it is a linear instrument, people give accuracy also. That's because of slight, I'm not very conversant. I use that term instead of this. They think it is okay. They use it. Okay. So you should understand. Okay. And here it is the linearity that's basically telling the accuracy of the instrument, weight and operating temperature, humidity, and what pressure you can use, what is the range of the instrument, all that data. So you should be able to read and understand what is the typical specification. Right. So far any doubt, the basic potentiometer for both linear type and rotary type I have covered. Any questions? Am I going too fast? Because 3-4 classes we are lagging as per the lesson plan. So there is a tendency that I am slightly speeding up my lecture than our usual pace. Any questions? It's clear? Able to follow? Next is the conductive plastic potentiometers. What is meant by conductive plastic potentiometers? It uses an item called magnetoresistors. An item called magnetoresistors. What is meant by magnetoresistors? Basically, there will be ferromaterials. When you take near to a magnetic field, the resistance changes. The resistance changes. Such materials are called magnetoresistors. Thermoresistors means what? When you heat, the temperature changes. There is no such thermoresistors, but it's only normally when you heat that characteristics changes. But when you take the ferromaterial to magnetic field, keep it in magnetic field, depending upon the direction of the field and the current direction, it offers additional resistance to the flow of current, and that increases or that basically changes the resistance of the ferromaterial. This property is called magnetoresistance. Okay. Normally a ferromaterial will have a mild self-resistance. That resistance will be there. That's by default. Any conductor will have some resistance. When you keep this in a magnetic field, the resistance changes. Whether the resistance is lower or higher in the magnetic field depends upon the direction of the current and the direction of the magnetic field. If both are perpendicular to each other, it offers the maximum resistance to the current flow. Whereas when the magnetic flow and the current flow in the same direction, the resistance will be minimum. Okay. Now we design a magnet which will create a magnetic field which is perpendicular to the direction of the current flow. Okay, and keep it ready. Such a magnetic field is available in this particular common magnet. It is a permanent magnet. Magnetic field goes perpendicular to the direction of the current. Okay. Need not be exactly 90 degree, but the magnetic fields, because the manufacturing is easy if the magnet is in the circular form. Simply you can finish. Exact 90 degree means special requirements are there that may not do. We will have a circular permanent magnet which will have magnetic field. Of course, need not be exactly 90 degree, but as the angle becoming closer to 90 degree, the resistance it offers because of the magnetic field is high. The lesser it comes to, the lesser the angle and comes closer to the direction of the flow of current, the resistance will get reduced to that extent. So we will have a permanent magnet, and there are two magnetoresistors, identical, same type, same size, everything is same resistance. So initially it will have some resistance, it will have some resistance. And here is the voltage that I am measuring. Here there is a negative voltage, here there is a positive voltage. Let's say here positive 5 volts, here negative 5 volts. Voltage supply we have source voltage. And then the output voltage is measured here, VO. Output voltage is measured here. Okay. Now the displacement to be measured is connected to this the permanent magnet. And when displacement takes place, the permanent magnet as a tube, as a cylinder that moves either towards right or towards left. Initially, when it is in the zero position, this also has enough magnetic field, this also has enough magnetic field. Identical magnetic field, identical type of ferromaterial, that's a magnetoresistors. So the resistance on the left hand side ring, on right hand side ring, for you, okay, both will be same. So whatever is the voltage coming here, the plus 5 volt, minus 5 volt, same amount of resistance. So here we will have some voltage, here you have some voltage, same size, difference in amplitude, and you will get the voltage output here, that's 0. You will have 0 potential. That is 0 setting. Even if it is not 0, we will adjust the position slightly and make it read 0. Once 0 setting is done, then the permanent magnet, the object whose displacement is to be measured, you connect it to the permanent magnet and move the permanent magnet along with the body. So permanent magnet moves towards right, your right, okay, your right side. So what happens here? This particular magnetoresistor is fully under the influence of magnetic field, like before. Whereas here, some part of resistor, is not greatly influenced by the magnetic field because the magnet has moved towards your right. Okay. So this will be less exposed to magnetic field. Magnetic strength will be less. So resistance decreases. Earlier, more resistance. Now, resistance decreases. So if resistance decreases, the more of positive voltage will go. Same amount of the negative voltage will come. Whatever is the voltage. Let's say this is minus 5 volt here, plus 5 volt here earlier. So that cancels and you get 0 volts. Now here you have then you should have a little higher voltage here. Okay. Then only 5 volts will get here. Earlier we got 5 volts. Now let us say you are getting 6 volts here. Here same 5 volt. Here it is minus 5 volt. Here it is positive 6 volt. Effectively 1 volt, proportional to the amount of displacement you will get as now. So as the resistance keeps increasing, you will find more voltage there because resistance decreases and you get the volt. Or other way around. Okay. The proportional to the change in the resistance, drop in the resistance, you will get the output voltage. By measuring the output voltage and calibrating to displacement, with respect to displacement, you will be able to measure the displacement. This is for a linear motion. This is for what we know. Same type. What you see, the semi-spherical shape, it's not exactly semi-spherical. It's like the mudguard of the wheel. You have some shape and then completely covered. Half of the wheel is covered. It's like a wheel. It's like a wheel. So here it is the positive terminal, here it is the negative. Whatever is linear, you just rotate it. It is actually the rotary type. The magnetoresistive type potential. Why we do all such exercise? Because there are a lot of problems associated with Viper. Why there is a lot of problem with Viper? Because it is contact type measurement. There is a contact between the Viper and the resistive element. That is avoided here. There is no physical contact between the resistor and the permanent magnet. There is no physical contact, no friction, no wear and tear. Okay, no lubricants are needed. Simply non-contact type. Hence, the problems associated with all the Viper related issues are eliminated. So you will be able to make better instruments out of this. Is this clear? Yes. Of course, its characteristics. It is non-contact type, infinitesimal resolution. Even in potentiometer, you will have infinitesimal resolution when you are not using manual. When you are not using manual, basic potentiometer you use, multi-turn potentiometer you use, all the design variation, infinite resolution you will get. The infinitesimal, very finite movement also you will be able to measure. Whereas in case of manual, when you use wire-wound resistors, when you use, then resolution you have to compromise. You are able to appreciate that, but your butt rate. What is your second part of the name? Check it. You understand how this manual will affect the resolution? But you didn't ask me. You're busy with something else. How many of you do not understand the effect of resolution, effect of manual on resolution? So suppose you have a wire. You have a wire. It's a continuous wire. You have a contact, and continuously you can move. Even the minute possible displacement, the Viper makes, there will be a proportional change in the resistance, and you will be able to measure. Suppose if I have a manual, and the wire is not a single wire like in the earlier case, it is wire wound like this. Okay, the resistive wire is bound on the manual like this. The Viper can touch the first winding, then it can only move on the top, as you might have seen in the rheostat. It cannot rotate. Okay, if it is rotating, that is multi-turn potentiometers, like the spiral. If the Viper is like this, as it rotates, it can go and touch everywhere. There, it can have infinitesimal resolution. I am talking about the mandrel on which the resistive element is bound and the Viper is moving linearly on top of the side. Monitoring, there is a mandrel and the Viper moves on top of it. Okay. In the process, what happens? Either it touches the first wire or it touches the second. From here to here, it makes a jump. The resistance corresponds to one complete winding. That infinitesimally, it is not touching all the wire completely. Either it touches here or it can touch only the next winding. It is not possible for it to go around and touch the winding. Because of that, when you make the displacement versus your change in resistance or change in voltage or whatever that you are measuring, that in the linear wire case, when potentiometer is continuously touching, it will be like this, linear. This is case 2, and a mandrel. It will be like this. Either it can touch the zeroth position or the first wire. Then it can touch only the second wire. Then it can touch only this particular length of the change in the resistance or change in the voltage is proportional to the change in resistance is proportional to the resistance of this. So let's say that is 0.1 ohm. So anything less than 0.1 ohm you cannot measure, because every turn that I jump from here, the resistance of this is 0.1 ohm, 0.1 ohm, 0.1 ohm, 0.1 ohm, 0.1 ohm, only you can jump. 0.1 ohm, any value less than 0.1 ohm you cannot measure using it, because you are jumping 0.1 ohm, 0.1 ohm. Here 0.1 ohm also you can measure, 0.11 ohm also you can measure, 0.12 ohm also you can measure. As you slowly move, you can measure infinitely small values. Where in normal potentiometers, wire wound, multi-ted potentiometers and things like that, linear potentiometers and things. Whenever it is bound on a mandrel and the contact moves on top of it, then it will not be able to have influence on the system. Is clear? Yes? Can you explain? Another graph. See, you pay so much of money to leave your parents in your home, long way, right? You must be from North India, right? And then come all the way to South India for what? For learning. When front benches are free, you sit in the back bench. That itself shows, you want to just slightly keep up with yourself. Why don't you come occupy the front seat, be very eager to learn? Come. It's not only for him, there are many others. Just instead of simply coming and sitting disinterestedly, think about your dad, how much effort he is taking to earn single rupee to pay for you. And so much of money is given to us, in turn it is to us, of course, and we are trying to do some justice. You should be able to grab as much as possible. Every day, once you tell before coming to the class, so that you come with a chart. See, I have paid 1,45,000, whatever. I don't know what is the fee you have paid. So much I have paid for this year. I will grab as much knowledge from this fellow, because I already paid money. So I have to grab. Come with that fire, so that you will be able to learn a lot. Morning, second, like that, you come dull, or come like Vitali, 10 minutes late, and then demand for attendance. No, Vitali, a girl who always comes late. Time it, 5 minutes. Okay, fine. So, every time I will not be cool. Sometimes I lose my temper so easily, and then you will have tough time. So don't depend on my temper. I have very bad temper. And that's consistently people have said. Sumaran sir is a good teacher, but he loses temper very sharply. I told you in the very first class, I am like that. So I try to change myself. It's very difficult. So you have to prepare yourself very well and then get into the subject. Once you are into the subject, you can see me as a good teacher. If you are out of the subject, then you will see me as a villain only. So whether you make me a hero or a villain, depending upon whether you come on time and you are interested in the subject. There are only two things that you have to follow. Right. The last item is optical potentiometer. Again, the problem is Viper. Viper had this problem, and we are trying to develop an alternate way of measuring displacement. Alternate way of measuring displacement. Okay. So you have to mentally be with me. It's not sufficient to sit in the front row. So optical potentiometer, you have a resistive layer, you have photoresistive layer, and a conductive layer. The conductive layer is not very much visible. Not just it's not visible, right? So try to focus. Here it's a layer, and here you have the reference voltage. Here you take the voltage. Okay. So conductive layer is like a conductor only. Okay, conductor only. Resistive layer is a resistive layer, no difference. But we had a physical contact or the Viper in case of normal potentiometers, whereas in optical potentiometers we have an optical Viper. We have an optical Viper. What is an optical Viper? I will just go to normal potentiometer. You see, There it is linear, right? So we go to linear. Yeah. This is conductor. This is resistive layer. What connects here is the wire, right? You see, this is resistive layer. This is conductor. What connects that is a strip of light. Strip of light, and that light falls on the photoresistive material. Normally the resistance is high. When light falls on it, the resistance decreases, and it acts as a conductor in that region. It acts as a conductor in that region, wherever the light is falling. So it is as if there is the wiper which connects the resistive layer and the conductive layer, but there is no physical touch. There is no physical touch. So all your contact resistance problem, the friction problem, all your vibratory environment problem that we encountered in normal, conventional potentiometer is all eradicated, removed, eliminated, and still we will be able to make it. So there is a change in resistance. Proportional to the change in resistance, there will be a change in voltage here. By measuring the voltage relating to the displacement, we will be able to. You are able to understand? Okay. Only difference between conventional and optical potentiometer is we are removing the physical wiper, putting an optical wiper. Optical wiper means what? A light beam which connects resistive layer and conductive layer. So it connects, gives connection. For rotary measurement, you use rotary shaft. For long length measurement also people use. Up to a few mm, 10 mm, 15 mm, 50 mm. Few meters also, this kind of rotary type potentiometers are used. We simply use a wire. In the land, they measure earlier olden type surveying. Also, people use this kind of transducers for measuring long distances. Potentiometer for long distances, because simply wire you have to use. Even low resistivity material you can use there. Simply take a wire, go 10 meters from here. Because 10 meters you have gone extra on that side, there will be a change in resistance. Measure the change in resistance relative to the dimension. Potentiometer, what is the advantage? Cost is very less. People are already manufacturing it in bulk quantity. Easily available everywhere. You don't have to apply, you don't have to buy it from Flipkart or Amazon or any online or what is it, services. You simply go to Tamram, you will be able to get one linear potentiometer. Simply go to outside of the university, any electrical shop, ask for potentiometer. In Kandigai, you will be able to get a potentiometer, a sensor which you can buy on the streets. That's the advantage. Availability, low cost, still reasonable good performance. Reasonable good performance. Disadvantage, of course, all that I have discussed. The contact force, friction, inertia, wear and tear, exposed to atmosphere that gets corroded, eroded, if the coatings are not good, all that about it.